The next talk is about the verification of function blocks, which is presented by Jackie Wong. Thank you.
Good morning, everyone. Unfortunately, this is going to be my final talk in this workshop. Unfortunately, this is an exciting paper to present. And just want to clarify that I actually got two affiliations back in Canada. So this is actually McMaster Center for Software Certification. So just to make sure, I'm actually the same person as yesterday, just with different affiliations. So this talk is going to be about how to actually examine an industrial standard and try to identify issues by using formal methods. And we did find some issues with a standard that has been used for more than 20 years. So we think that should be a valuable contribution using formal methods. Okay, so that summarizes our motivation and background. So we actually have the Ontario Power Generation Company as our industrial partner. And at the moment, they are actually undergoing a re-engineering process to refurbish their design and requirements of the Darlington shutdown system. There are two shutdown systems, actually. At the moment, they are thinking about to replace the existing implementation with function blocks. And function blocks are the basic abstraction units for implement PLCs, programmable logic computers. I'll give you more information about it. So since they have such intention to replace the existing implementation, there are two important questions to be addressed. First, because you're not going to use one single big function block to implement the whole shutdown system, you're going to use a composition of multiple function blocks. So the first question is the system behavior resulting from function block composition going to be predictable? That's the first question about predictability. The second question is, does a vendor's function block implementation conform to its requirements? Because the OPG later on is actually going to use function block implementation supplied by some tool vendors. But how can they make sure that the implementation itself is actually conforming to the requirements? So these are the two questions. One is at the requirements level. The other one is at the implementation level. We're trying to address both in this talk. So our proposed methodology or approach is to use formal methods. Particularly, we're going to use tabular expressions, which is a way to document complex relations by using a two-dimensional table. We actually saw that example yesterday, but I'm actually going to show you a different example today, a more realistic example. And the second tool we use is called the PVS, Prototype Verification System. It is actually an interactive environment for writing specifications in higher order logic and to use sequence-style deduction to prove theorems. So why are we bothering with formal methods? There are two compelling reasons for using formal methods. The first one is we actually want to have shared requirements between tool vendors and the users. And the users, in this case, being the OPG. And the second one is, once we have a shared requirements between the vendors and the users, we want to make sure that for any candidate implementation provided by the tool vendor, it can be verified with respect to the shared requirements. So those are the two reasons why we bother with formal methods. And we actually do two case studies for our approach. The first one is addressing this paper, which is about the IEC 61131 standard on function blocks for PLCs. And some extended work that we're doing is to examine the possibility of doing model-driven engineering for the requirements documents of the shutdown system. Because the requirements is actually specified using tabular expressions, and how can we actually automate the process to transform from tabular expressions into function blocks and prove that the transformation is correct. That's also the extended work we're doing. Okay. There are actually three things to talk about in the context. The first one is the standard of IEC 61131. That's where we do the case study to examine if their function blocks are precise, are they correct, and are they complete. And the second context would be the tabular expressions, which we use for formalizing the function blocks in the standard. And the third one is the PVS proof system for doing proofs. let's just go very briefly about the background before we talk about the methodology for the paper. First of all, this is a summary slide for the standard. So IEC 61131 Part 3 is actually a standard on a real-time and embedded system running the PLC, programmable logic computers. And function blocks are the basic units for implementing PLCs. And there are three types of function blocks. The first one is called the basic functions without any internal states. And the next one is the atomic basic function blocks. And the third one is the composite function blocks, which reduces the basic functions for basic function blocks. Let's have a look at some examples to make it clearer. So for the basic function block, let's consider the hysteresis function block. So anyone heard about hysteresis before?
Oh, yes.
Okay, good.
But I still don't know what it is.
Okay, that's fine. Either you heard the term or not, that's fine. So basically, the hysteresis has, okay, so for the standard, this is the point I want to make now. The standard is actually very, very informal, and they supply hardware-oriented implementation. Usually, this is the first information you get from the standard, which is the declaration of the function block. In this case, we have the hysteresis function block. It has three inputs, input 1, input 2, and the hysteresis band. And all of them are real numbers. And this is the output Q of type Boolean, which means should you trip the alarm or not. And the input is a set. So let's just consider this intuitive diagram, how we should understand the hysteresis behavior. So let's imagine that the x-axis is the time, and the y-axis is the value for the first input. So imagine that the first input is some sensor value you're trying to monitor, and the second input is actually a set point that you set for your system. So you continuously monitor the value for the sensor value, and if you actually, so this is the set point. If you actually go above this level here, so we have the this set point plus the hysteresis band. We have the set point minus the hysteresis band. That's why you see the whole band is actually 2 times the hysteresis value. So if you actually, if your sensor value is actually strictly larger than that, then you will trip the alarm, set it to be true. If it is strictly smaller than that, you will trip the alarm by setting it to be false. Otherwise, if you're within this region, it's actually flexible, so you just, there's simply no change, just equal to the value in the previous state. Okay, that's the function block. So that's the hysteresis function block. It's a basic function block. Let's just go back to our introduction here. So let's have a look at the composite function block, limits alarm. And guess what? The limits alarm is actually going to use the hysteresis block. So that's why I said, you can reuse the function blocks in the standard for the composite function block. Without going too much into the detail, let's just have a look at the declaration for the function block. So in this case, we have a high limits, we have a low limits, and we have also the sensor value, and we also have the hysteresis band. So it behaves very closely to the hysteresis, but we're just considering 2 limits. Okay, so this is sort of the mathematical relation between the two. So let me just give you a little bit more intuition. So this is actually the limits alarm. So you can see that we actually have this part using one hysteresis block, and this part using another one to calculate. And yeah, without going too much into detail. So that's sort of the behavior you expect intuitively. Okay? Go back. So that's sort of the 3 types of function blocks we have in the standard. And now, the standard usually supplies 1 or 2 possible implementations for the function block. One is for the structure test. The other one is called the function block diagram. The one we just saw for the limits alarm is actually function block diagram. And for the structure text, it's simply a block syntax like Pascal. I'll show you some examples later. What we have achieved is we have formalized and verified about 80% of the standard, and we have found 5 issues. And those issues can be classified as either ambiguities or missing assumptions, or even worse, there's some errors in the implementations. Given that the standard has been used for more than 20 years, they actually released a new version about several months ago this year, or last year. Okay. What happened was they removed the whole function block library that we tried to examine, but some errors are still there. They just haven't fixed them. Okay? Okay, just with tabular expression, I'm pretty sure every one of you has seen the tabular expressions already. So without going too much into the details for this, let me just show you one example very quickly. I'm actually going to reuse that example later in the talk. So the tabular expressions have been successfully used in the nuclear domain in Canada, namely the Darlington shutdown system. So this is one example. So this guy here behaves very much like a hysteresis we saw before. The only difference is about how we handle the boundary value. Remember I said before, if the sensor value goes strictly above the set point plus the hysteresis band, we'll set it to be true. In this table here, we actually are less, is at a weaker condition. If it is just on the boundary, we will have to set it to be true as well. That's the only difference. So this is just one example to present the tabular expression. So you have different conditions. They are both complete, meaning that there are no missing cases, and they are also disjoint, meaning that for any arbitrary value from the inputs, you have only one row that will satisfy the input condition, and you will set the output value accordingly. Okay. Just come back. So that's pretty much about the tabular expression I want to say. Okay, let's go to the next one, which is about the PVS. I wouldn't talk about in detail how we actually do the proofs in PVS. It's actually available on our website. You can get all the PVS scripts over there to try out if you like. So as I said before, you specify a proof in PVS environment. And the thing I want to mention is, in PVS, one of the reasons we chose PVS was because they have direct syntactic support for tabular expressions. You can directly specify tables. And those completeness and disjointness properties will be automatically generated as the proof obligation for you to discharge. So that's one of the main reasons we chose PVS. And also, in the literature, they also applied the tabular expressions in the Darlington shutdown system. If you're interested, you can have a look at the paper. Okay, this is the most important slide for the talk, which summarizes our methodology. You see that there are actually 2 boxes. The first box represents the domain of the IEC standard, and the right-hand side box represents the semantic framework of PVS when we do the formalization and proofs. So there are actually 3 manual formalizations we do. The first one is based on the natural language descriptions or any information we can get from standard. We are actually going to formalize each function block into a tabular requirements in the PVS. Okay? And for each function block, the standard may supply either the ST implementation or the function block diagram implementation, or both. We're going to translate them into individual specification in the PVS. Okay? So now, all the 3 artifacts are now in the same semantic framework. What we do is to perform 3 kinds of proofs. The first one is to make sure that implementation actually implies the requirements. That's called the correctness proof. The second one is to make sure the implementation itself is actually feasible. The third one is to make sure if you have 2 implementations supplied by the standard, you better make sure they're consistent with each other. That's called the equivalence proof that we're performing. Okay, so we have 4 contributions in this paper. So we formalize the requirements for each function block in the standard to have unambiguous behavior. And the second contribution is we also formalize the implementation for the structure test and function block diagram by the standard. And we also proofs about the correctness, consistency, and feasibility, etc. The fourth one is we found issues in the standard. I will actually briefly talk about one issue in detail. Okay, so now let's just have a look at how we actually formalize the requirements and implementations in the standard. So this slide is exactly what I said. So we have tabular requirements for each function block, and we have formalized the two implementations in PVS, and we also, so that they're actually the same semantic framework to do the verification. Okay, so this is actually a hysteresis function block we saw before. This is the diagram I used to give you the intuition, and these three tables are our formalization for the function block. And without going too much into detail, I just want to show you that. So we actually have three tables here. They have some implicit data flow between them. So if you want to evaluate the tabular expression, you should always look at this first. So the final result for the trip along depends on the lower along and the higher along. If either one of them actually trips, then you will trip eventually. Otherwise, you will just say not trip. Okay? And we also have some assumption over here just to say this region here is actually non-overlapping. Okay, more details are in the paper. I just want to show you, by using tabular expression, we can have a very complete and disjoint and precise specification of the function block. Okay, so the hysteresis block was actually supplied by some structured text implementation. So this looks just like normal programming text. And we actually translate it into a tabular expression. So you can think of this is just the first if branch, second one, and third one. And we just have, I'm pretty sure you prefer this documentation here as opposed to this one. It's actually much clearer to actually see what's the intended behavior of the function block. Okay, so now to actually formalize the function block implementation, let me just bring you back to the limited along. So this is the function block diagram implementation for that. So you can see it is actually a composition of 1, 2, 3, 4, 5 internal blocks. So the way we do it is to say for each internal block, we are going to formalize it as a predicate, as a relation between the inputs and outputs of that internal block. And because it is actually a predicate, so we can just compose the behavior together by taking the conjunction of each of the internal blocks together. So that's the formalization. That's the detail I want to show you. And we also prove that the behavior is actually deterministic, which each one of them is deterministic. Okay, so these are the three kinds of proofs I just mentioned. So we prove correctness, we prove consistency, we also prove equivalence. If you're interested in how exactly those proofs are done, please refer to our website. We actually have all the source scripts over there. That's all you have to know for this talk. Okay, so our first case study, so that up to now it was our methodology. Our first case study was to examine the IDC 64131 standard, and we have found so far 5 issues. So we have found some ambiguous behavior for timers. We have some ambiguous time delay, missing assumption, and we have some errors in the implementation. So all of them have been documented in detail in our technical report and also in this paper. So please read them if you are interested. And more importantly, for each of the issues that we found, we also suggest resolutions as to how we should solve them. And let's go very quickly on one issue. This is actually quite a complicated issue, so I don't want to spend too much time in this talk. But the thing I want to mention is, this over here is the only information we got from the standard about what should be the behavior for the timer. So this timer here, so this is like a timing diagram just to show you that. So you have the input in and you have output Q. and what should be the output Q value be as opposed to the input value. So that's the only information we get from the standard, and it is extremely limited to a very small number of use cases. So we actually raised 2 questions here. So let's not worry about them. You can read the paper for the questions. So we actually raised these 2 questions, which cannot be found for the answers in the timing diagram. So what we did, as you can expect, we actually formalized the timing behavior that we thought should make sense. So this is the tabular expressions that we have for formalizing the timing behavior. And once we have got these tabular expressions for each of the 2 issues that you saw on the previous slide, we actually have a unique path in the tabular expression to resolve the question, to actually tell you the answer. Okay, that's all I want to say about this case study. Let me just go very quickly on the second case study we do, which is about the model-driven engineering for the shutdown system. Before I do that, let's just show some relationship between the 2 case studies. In the first case study, we actually formalized and verified or certified the function blocks in this standard here. Well, the result is our repository of PVS specifications and proofs, and they are compositional and they are formal. We can certainly reuse this repository and do some model-driven engineering for the shutdown system. So given the requirements documents for the shutdown system, we can actually argue about the correctness of the model transformation into the function block implementation. Let me just give you some example just to convince you that it can really work. Okay, exactly what I said. And let me just show you one example. So this is the block, the tabular expression we solved for. So this is taken from the requirements documents for the shutdown system. We want to increment this by some function block. Okay. There are 2 possible implementations for this, and we want to argue the correctness of each one of them. The first one, because you can see that you can simply interpret this as some if conditionals. So you can just use the selection blocks from the standard. The second one is you can use the hysteresis block that we have just certified in the previous slides. Either way. Okay, the first one is simply 3 selection blocks to increment the 3 rows of the input conditions. And we can also reuse the completeness and disjointness properties for the tabular expressions. I won't go too many details into it, but what we want to prove is the function block implementation behavior would entail the behavior of the tabular expression requirements. Okay, I'll finish that up in 2 minutes. Yeah, so this is the first possible implementation we can do, and we can certainly prove this theories because we have all the specifications already in our repository for the case study 1. So this is really handy to prove and has the very great practical value. The second one to do is, since we got the hysteresis block pre-certified already from case study 1, so why not we just reuse it? However, the story is not so simple because, as showed you before, the boundary cases between that tabular requirements and this hysteresis block are not exactly consistent. So we have to somehow adapt the result from one to the other. So this is the precise mathematical relation between the 2. So if you want to calculate this sensitive value, so it is equal to the hysteresis block plus some other massaging of the output results. Don't worry about details. So that's just an overall picture I want to show you. The implementation is not that straightforward. We can certainly do that precisely and to verify its correctness. Okay, so we have 2 implementations, and we can actually verify the correctness of both of them. And that's actually the function block implementation we have for that second case. And it looks quite complicated, but since we put everything into PVS, into a formal semantic framework, we can certainly argue their correctness. That's the value about model-driven engineering, really. Okay, so that's the conclusion for this talk. We have, so this is, again, our methodology here. We have formalized using tabular expressions on the standard for each function block. And we have done verification in the PVS proof environments. And we also demonstrate the value of our approach by finding issues in a standard that has been used for more than 20 years. No one has found it. We found it. And we also I show you that our extended work actually used a sound foundation for our case study one from the standard to actually support model-driven engineering for implementing the tabular requirements using function blocks, and we are able to prove the correctness. And if you want to find some references, we have an extended technical report for more issues found in much greater details. And we also put all the PVS specification and verification scripts on the website. Thanks for your patience.
Jackie, have you got any questions?
Yes.
So just that these issues found is their ICE 1166 and so on.
61131.
And yeah, so are these sort of minor issues of imprecision, or are they sort of major things? Because the minor issues are serious.
Yeah, I would say so far, okay, we have found 5. So 4 of them are like imprecision under specification because they don't have, well, they haven't put some assumptions on the input such that you cannot prove the correctness or consistency with the requirements. And the one that we found being an error is they actually have a structure text and function block diagram for the stacked integer function block. What we found was they actually have a missing function block in diagram. That's something, while they can argue that it's a typo, but they haven't fixed that for up to 20 years. Yeah. But I would say our approach is mainly to formalize and try to, make.
Well, I mean, it's good if you get something, some concrete stuff to show people, right? So after formalization.
Yeah. Yeah. So the concrete stuff is we can present, tabular requirements saying this is how the true event should increment.
And have you talked to these people behind, or 20 years ago? I don't know.
People in the standard?
Yeah, or whatever. Just do somebody, right, who actually appreciate this result.
As far as I know, maybe not. Yeah. They might just argue that they just don't bother with putting the information there. But one thing to note is the information they put into the standard is actually very hardware oriented. They don't actually, it's not really like a standard for requirements or specification. It's really like a standard for hardware implementation. Yes.
Okay. So these function blocks that you presented are analog or digital components?
Actually, that's a good question. Analog or digital? I think they should cover both because I think the function block should be above that level.
Because I asked this question because you see you take real data in those functional blocks, and I was wondering if they're digital, then there may be some computer arithmetic round of errors in there when they're comparing to real numbers.
They do have the real numbers in the input and output, but whether they're analog or digital, that's something I'm not sure about.
Because if in implementation they are implemented using the digital technology, then they may have some round of errors.
Yeah, actually, yeah. So the function block diagram or structured text they provide as the implementation is not really like the final implementation you would have. So I think the issue you just mentioned may be even lower level.
Yeah.
Which I think that will actually down to our tool vendor. So actually OPG, they have the ready tool vendor for function block. So I think that's some issue we have to make sure for them. But for that, I'm not too sure to actually make sure their tool implementation conforms to our function block behavior. For that, I'm not exactly sure how practical it is to do verification. Maybe we have to do extensive testing to make sure you have no run of errors, etc. That's something to be explored further. Yes?
So with these sort of inconsistencies and ambiguities you found
Sure.
in the timing, is it the act of modelling that uncovers these and then the modelling itself that gives you the details of them? Or do you only sort of discover them once you've completed the model?
Okay, sure. So if I just bring you back to this diagram here. Yeah, so basically when we look at this diagram, when we first read the standard, we thought that's ridiculous because we are kind of from the computer science or engineering discipline. So we thought this is unacceptable. It's a standard, and we just thought about, are there any missing cases, for the timing behavior? And we just thought about these two, and then we thought, okay, if these are at least two, ambiguities from the missing scenarios from the diagram, then how can we do about it? So our colleagues actually did some previous work about defining the timing tolerances or timing behavior using tabular expression. So that's how we actually just use the tables to specify. I think that in some way, you can think we are proposing one possible formalization that may not be exactly what the people in the standard intend the behavior should be, but at least you have something that's unambiguous to be shared and to argue about. Yeah. Let's say if the people from the standard, as Peter mentioned before, that if we talk to them saying, okay, this is how we think your behavior should be, if they said, no, that's not the case, we intended the other one, we said, well, at least you can see how our intention is, and if you want to change the behavior, we can just give you another tabular expression to do it.
Got it, as you said, verified 80% of the standard.
Yeah,
How hard is it to do the remaining 20%?
That's a very good question. So I am not the main person who did the specification and proofs. It was actually Lena, the first author, who actually did the work. So it seems like, we actually have got another 6 function blocks to be verified. So I think the difficulty is mainly about how you prove, when you actually have both the structured text and function block diagram implementation, it's kind of difficult to actually argue about the equivalence or sometimes implication. Because sometimes they may not even specify the implementation at the same level of abstraction. So one might be quite high level, the other one might be more variables about hardware. So it's kind of difficult to argue. But Lena kind of promised that she will finish them by the Christmas time. Or, something like that. But I would say, we should anticipate that the remaining 6 should be actually verified in a pretty much same approach. Shouldn't be